Can you see this? This is half of a football. And I put the, it's a bit different. I put the two halves together like that. I can try anyway. Put the two halves together to make a complete sphere. Alternatively, I could take this iPad and I could put this on here. Okay, now when I put that on there, it's actually, now it's quite stiff. Whereas when I've got it like this, it's really very, very flexible. Now, I suppose the first person who looked into this was Raleigh. He wrote a paper on bells, Lord Raleigh, because if this was a bell, you hit the bell and it would oscillate. And when it oscillates, it bends, but it doesn't really want to stretch. Now, if you've only got half of a sphere like this, it is very flexible and you can roll it up. And what happens when you do that is that the Gaussian curvature remains constant, which is the product of the two principal curvatures. And you can see it gets much more curved this way and it becomes less curved that way. If you have a complete sphere, then what the convulsion theorem shows is that you can't deform it at all without changing lengths on the surface. The problem is, though, that if it's a very thin sphere, then it can buckle, which basically means that you get a small amount of extensional deformation and a large amount of bending. Here we have a grid shell, and this is made of a woven wire mesh, and this is actually quite flexible. And the reason it's flexible is because it's only got wires in two directions, and when I load it, the squares on the surface become diamond shapes. And this is very similar to the Essen model that we built. In fact, you could take this and you could put some loads on it, maybe like this coffee cup and so on. And from that, you could predict how a structure like Mannheim would behave by scaling the results. Do you want me to tell you how to scale the results, or do you know how to do that?
I don't know.
Okay, it's very easy. Let's imagine that you built a large structure which was a perfect scale, a perfect scaling up of this. So it was made from steel and all dimensions were increased by, say, a factor of 100 or something. So the span was increased by 100, the diameter of the wires was increased by a factor of 100 and so on. Then if you did that, then dimensional analysis, that's like Reynolds number and all that stuff, would tell you that the full scale structure would carry exactly the same load per square meter as the model in kilonewtons per square meter or whatever. So that means that there's no scaling required at all, and provided that the loading per square meter is kept the same. But then you say, actually, this is made of steel, whereas my model, my real structure is going to be made of timber, say. You then say, I'm probably mainly interested in the Young's modulus, the stiffness. And so you then scale your result according to the Young's modulus of timber versus the Young's modulus of steel. You might then say, actually, my member sizes are a bit different. I haven't scaled those. So you then say, it's probably the EI value that I'm interested in, and that the collapse load is proportional to the I value. So if you make the members twice as big, the I value goes up say, a factor of power 4, which is 16. So you'd then say that you'd factor the load by 16. If the spacing was different, you then say, well, double the spacing, I'd probably half the load, in the sense that I'd be reducing the bending stiffness by a factor of 2. So that's basically how we scaled the results on Mannheim. Now, what's really interesting about this is you can see that because this has got this extra flexibility, it does actually, the load is still going up even after these really big displacements. Whereas this is much stiffer than this, because it's fully triangulated. I'm going to be a bit careful now. When I load this, the load is very stiff, and then the load suddenly drops, and the load is really dropping. So this is very imperfection sensitive, but very efficient, whereas this is less efficient and less imperfection sensitive. Okay, so that's the Convos theorem for you.
Why is bending stiffness more important to stop shell buckling?
They're both important, both bending stiffness and membrane stiffness, but the buckling load is roughly proportional to the square root of the product of the two. Increasing the membrane stiffness is the most efficient way of doing it, but it also leads to this imperfection sensitivity. And of course, the other thing is that it's not just the shell itself, it's the shape of the shell, which normally aren't just spheres, but it's also the boundary support. Very often roofs, like the British Museum roof, are on sliding bearings. So it can't thrust outwards, it just expands. And that makes it a lot less efficient. We did some of the grid shells by Schleich. Some of those have got tension ties inside. And we tried to persuade Foster's to allow us to put tension ties in the great court, which would have made it more efficient. But it probably looks better without them. But these decisions are very difficult to make, and you have to make them very often quite quickly. And since that time, lots of people have done various studies on the great court, investigating different grid patterns, for example.